Welcome to our discussion on logarithmic equations. Let's start off with just the fundamental properties of some of these kind of special logs. So one of the more common uses for the log, and when I say log, I mean the regular old base 10 log, is earthquakes. Earthquakes are on a log scale. So when we talk about a magnitude 4.3 earthquake, that 4.3 comes from a scale that has a formula that involves a log, and this is the formula, right? So the energy related to the magnitude of the earthquake is given by this scale. You basically take the log of the energy, then you subtract 11.8 from it, you take that number, you divide by 1.5, and that gives you the magnitude of the earthquake. Okay, so if we want to answer the question for, what was the energy that was given off by a certain magnitude, well, then you're basically just solving for E. And getting log E by itself is pretty easy. You multiply by 1.5 to get rid of that fraction. Then you add the 11.8 to one side, and now you've got log E all by itself. That was some pretty easy, basic math. But how do you get the last step, right? How do we undo log E? Well, you have to remember that logs, whatever the base is, a log is an inverse function of an exponential to that same base. So log, log, without any number there, we assume that that's base 10, right? If it was base 7 or anything other than base 10 or base E, there would be a little number down there. And then, of course, base E would be natural log, and we would have a little ln there. But because there is no number here, we know this is log base 10, right? It's like we have a little invisible 10 down here. And so to undo logs, you basically have to do exponentials. So in essence, what you're doing is you're doing 10 to all of this stuff equals 10 to all of this stuff, which is just a basic math principle, right? If x equals 3, then isn't 10 raised to the power of x the same thing as 10 raised to the power of 3? Yeah, because x equals 3. So by substitution, I put a 3 in there and I get 10 cubed equals 10 cubed, right? So this is like a legal math rule. It's just like multiplying both sides by a number and that type of thing. Well, on the left-hand side, that's obviously just 10 raised to the power of all this, right? It's kind of hard to see the way this is written, but that's what that means. This is 10 to the power of all of this stuff, right? So you can think of it as kind of in parentheses. And then remember that 10, when you have the base equals the base log, so 10 to the log base 10 of E, they undo each other and you just get E. So that's how we undo logs, is we just raise them to a power. So if we had, let's say, log base 3, of x, and we want equals, let's say, 7, and we want to solve that, then you would do 3 to all of this stuff equals 3 to all of this stuff, and this would undo the logs, and you would have x equals 3 to the 7th. But remember, just from the definition of a log, you could have figured that out, right? Because if we have log base 3 of x equals 7, remember our trick of these little circles? Right, so 3 to the 7th equals x. Oh, look at that, 3 to the 7th equals x, right? So that's where that circular trick comes from. It's just a shorthand of realizing that to undo a log, you're just doing exponentials, right? Raising things to powers. And then, of course, now it's just a matter of plugging all that junk into a calculator and getting an answer. And you can see that you get a rather large answer, right? So because of that, we know that there's an awful lot of energy being expelled during an earthquake, which is, why buildings topple and things like that. Okay, so to remind ourselves of, how we can do these things, we have to remind ourselves of the two fundamental properties of logs. And it's basically that if you have log base b of b to the x, you just get x, because log base b of, again, b to a power, they undo each other, right? And then b to the log base b of x also gives you x, right? So these two things are really very strongly related. This one's kind of a silly version of it, because how often is this going to happen? Almost never, right? This is the one that's important. It's basically, how do we undo a log? Because really we learn all this junk so that we can solve things. And when we get different equations in different formats. We have to use different tools to solve them. And so whenever you're faced with some sort of equation you're trying to solve that involves logs of any base, you know that you basically have to isolate that log. You'll remember from our previous slides that we did all this math to get log all by itself. That was the first step. So it doesn't matter what the base is. It doesn't matter what the equation looks like. Getting to that point is always the same thing. It's like your first signpost you have to hit. The first thing I have to do is I have to unwrap this equation and move everything around so that I get one log all by itself. So you might ask, okay, what if you have multiple logs? That's okay. Just isolate one, use this trick. It will get rid of that log, and then you can work on the other one. You can also, combine logs. Remember we had rules for combining logs, and that's even the best if you can use the rules for combining logs and get it all into one log and then isolate that one log. That's the best way, right? But isolate your log, do the powers of both sides, and then solve whatever's left. So that all hinges on knowing the fundamental property number 2. So let's see if we can evaluate a few of these very quickly. Well, the first one should be easy, right? Because that's log base 10 of 10 cubed. And duh, that's just 3. Same thing with natural log of e. Well, natural log, remember, is base e. So again, natural log of base e, which is log base e of e squared, is just 2 as well. So 10 to the log of 8.3, those also undo each other, right? E to the natural log of 4.5 undoes each other, right? So all of these things are just showing you how it doesn't matter what the base is and whether it's a power to a log or a log of a power, right? As long as the bases are the same for each piece, they just undo each other. It's like squaring a square root and you're just back to whatever you started with. Okay, can you take the log of both sides and will it be equivalent, right? So we know we can multiply both sides of the equation by something. We know we can divide both sides of the equation by something other than 0. We have all these kind of math things that we're allowed. Well, the short answer is yes, absolutely. As long as your base doesn't equal 1, right? Because we really don't have a log base 1 thing. You can take the log of two sides of an equation, and those two things will be equal. Now, the way this theorem-y thing is written, it kind of seems like it's going in the opposite direction, and it is. But what it's really saying is that if you have a equal b, if you take log of any base other than 1, because that one doesn't exist, right? So log of any base, they're also going to be equivalent. And then vice versa, right? If the bases are the same and you have one log equaling another log, the only way that is true is if the two numbers are the same. Okay, well, with that in mind, we can define some further laws of logarithms. So if you're taking log of a product, you can split that up and make it the sum of two separate logs, right? Log of a quotient, right? A divided by b is just log of a minus log of b. And these two come from each other because remember, if I divide by b, isn't that the same thing as multiplying by b to the negative 1? So this would become, right, this one would become a times b to the negative 1, which would be log of a plus log of b to the negative 1, but this rule here tells me if I have a power, the power comes down in front, and that negative 1 would be out here, and that's where we get minus, right? So these two really come from the same thing, and then the power as well. So these three rules let us split up logs. So you take a log and you make 2 of it, but more importantly, for most of these things, you would go in the opposite direction. You'd be given an equation with a bunch of logs. You would use all of these rules of logs to kind of collapse them down to 1, because remember, if we can get one log and then isolate it by itself, then we can solve that equation. And that's really what all this stuff is all about, is being able to solve more types of equations, more, kind of convoluted, fancy equations rather than just standard old stuff. Now you can see the proofs of these things very easily if you just look at powers, because we know power rules. If we have b to the x times b to the y, it equals b to the x plus y. So if you kind of do a substitution, let a equal b to the x, let b equal b to the y, then we have a times b equals this, right? Because it equals those two things, which we know from the rules of exponents, equals this. Well, these two things are equivalent, and we know by rules of logs, if you take the log of those two things, right, they're also going to be equivalent. And so when you do all the work, you can prove it by taking logs and see what happens and how things cancel out. Now, most of you probably don't care, to see the proof of these, but if you want to see it, just pause the video, read everything, and go through it. But the bottom line is they work very similarly to rules of exponents, right? Because logs are inverses of exponential functions, so they should have very similar rules. This last one's really easy because it just comes from, if we've already proven that log of a times b equals log of a plus log of b, then log of a to a power is just log of a times a bunch of different a's, and based on that simple rule of it just becomes log of a plus log of a plus log of a, and it'll be p of them, then that's where you get p times log of a, right? So that one comes from that first one very easily. Now, when logarithms are used for calculations, we can break things up, we can bring them back together, and a lot of times that was what was needed in the past, but calculators have kind of made that necessity obsolete. So today, logarithms are really more important for solving equations, like we said. And so instead of breaking things up, you're going to want to contract them all together and make it one log. So when you have something like this, part A or part B, and let's say it equals something, and you're trying to solve it, you need to squish it all together and make it one log so you can solve for those variables. So let's look at the rules and see how we can do it. Right? First of all, you have to have that the logs are the same base. These are all logs, so those are all base 10. These are all log base 2, so those will be fine, right? So for the first one, we can go ahead and combine stuff and use our rules. This becomes the power, right? So that's the first thing we do is we bring the powers up. Then, using the addition and subtraction, right? So something plus something becomes multiplication, and then something minus something becomes division. So there's my multiplication, and then finally there's my division, and now I have one log, and I'd be able to do 10 to that stuff equals 10 to whatever the other stuff is, and then the log would go away and you'd be able to solve them. Same thing here, a little longer process just because there's a lot more to it, but really it's the same idea, right? The first thing we're going to do is deal with the powers, right? So you always want to do the powers first. Once you have the powers, go through and deal with the addition, right? Which becomes multiplication. And then do subtraction, right? So we have this one minus this, but we have plus this. You see how these two go together with the pluses? That's why they're on top. And then this minus puts it on the bottom. And that's it. I mean, you could obviously reduce. The x's will reduce. But other than that, that's all you got. Okay. How about proving the change of base theorem? Again, if you don't care, skip ahead. So if we let y equal log base a of x, we're going to do simple substitution. Then, by definition, right, doing our little circular thing, a to the y equals x. That's easy. Okay. Log base b of a to the y equals log base b of x. That's just taking logs of both sides. So now we can see that part of this equation, log base b of x, can be substituted out. We also know that this rule, right, brings the y down, and then we have log base b of a, which is the bottom piece. All right. So now look what happens. You can divide both sides, right? So all we did was divide both sides by log base b of a. And so there's your log base b of x over log base b of a, and you're just left with y. But remember, what was y? We defined y to be log base a of x, so we substitute that back in, and there you go. And that's everything we need to know for logarithmic equations.